Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 8, 2025, just 2 days ago. This paper introduces a new 8 billion parameter model that achieves performance comparable to much larger models like Claude 4 Sonnet. The paper is titled AutoTriton, Automatic Triton Programming with Reinforcement Learning in LLMs. And this breakthrough could be a foundational step toward building more efficient AI systems. It uses a clever two-stage process, combining supervised fine-tuning and reinforcement learning to automate GPU programming. So the authors visualize this process, which starts with gathering data. They take code from PyTorch, a common machine learning framework, and translate it into Triton, a language for writing fast GPU programs. This data is used for supervised fine-tuning, an initial training stage to teach the model Triton's grammar. Then, it moves to reinforcement learning. Here, the model generates code and gets feedback from a verifier that checks if the code works and if it's valid, for example, by ensuring it includes the @triton.jit decorator. This reward loop helps it learn through trial and error. Building on that, this next figure shows the data gathering pipeline in more detail. So to teach the model, they first need lots of examples. They start by collecting PyTorch kernels, which are small, optimized programs for specific tasks, from sources like GitHub. Then, they use two parallel methods to create Triton code. One path uses an LLM with specific instructions and chain-of-thought reasoning, basically making the model explain its steps. The other path compiles the PyTorch code and then uses an LLM to clean it up. This dual approach creates a rich data set for the initial training. Okay, so after gathering all that data, the real question is, how well does the model actually perform? This table then shows the main results on the kernel bench benchmark, which tests how well these models generate code. It measures two key things: compilation accuracy, which checks if the code is valid, and execution accuracy, which checks if it runs and gives the correct answer. And looking at the results, AutoTriton is a standout. Despite being just an 8 billion parameter model, its execution accuracy is the highest in 2 of the 3 difficulty levels, beating even huge models like DeepSeek. Alright, moving to a different test. This table shows the results on the Triton bench benchmark, and here again, AutoTriton really shines. On the right, in the Triton bench t-test, it achieves the highest scores for both call and execution accuracy. That's the 40.36 and 39.16 numbers, beating models that are vastly larger. What's really telling is the last row, which shows the model trained without reinforcement learning. Its scores are clearly lower, which proves that the reinforcement learning stage is the key ingredient giving AutoTriton its impressive performance advantage. And to prove just how important the specific design of that reinforcement learning is, this next table isolates one key component: the rule-based reward. It counts how often different versions of the model forget to include the @triton.jit decorator, which is a required keyword for valid Triton code. The full AutoTriton model is very reliable. But when you remove the rule-based reward, a system that penalizes the model for breaking syntax rules, the number of errors jumps significantly. This detail shows the reward system is crucial for generating correct, valid code. So we've seen that both the reinforcement learning and the specific reward rules are vital. But what about that very first training phase, the supervised fine-tuning? This plot really drives home its importance. It shows the training rewards over time for 2 models. The blue line is the full AutoTriton, and the orange line is a version trained without that initial supervised fine-tuning stage. The difference is stark. AutoTriton starts with a much higher reward and learns faster, showing that this initial stage gives it a crucial head start for generating correct code. So to wrap things up, what we've seen is that AutoTriton provides a really powerful new way to automatically generate optimized code for GPUs. The key is its 2-stage training process. First, that supervised fine-tuning gives the model a solid foundation in the Triton language. Then the clever use of reinforcement learning with rule-based rewards allows it to explore and find correct, high-performance solutions, even outperforming much larger models. It's a promising step towards building more efficient AI systems. That's all for this week's AI Research Roundup. Thanks for tuning in.